All right, let's do this, ladies and gentlemen. Have a piece of paper out to write some of this down. It'll help keep you entertained and alert. I know we are all jonesing for some lunch, right? We are looking at probability. All right, probability, random variables. Those kind of two go together. We've got two chapters here, chapter 5 and chapter 6 in this unit, all about probability and simulations and random variables and what we can do with those for stats. Hopefully you got a kick out of the comic there. A little frustrating scenario there, but just because there are two outcomes to something doesn't mean that it's a 50-50 chance between the two. One could still be more likely to happen than the other. That's a kind of a humorous take on that. But probability, you probably have done a lot of probability before. We kind of go a different direction oftentimes. Probability that you've done is oftentimes, oh, there's marbles in a drawer or something, and marbles in a bag, and you draw out marbles. What's the probability of getting a red marble kind of thing? And we do some of that. That's true. But there's so much more than just that type of probability, especially in how it relates to statistics. So there is a Nearpod link. If you didn't see that in the general channel, you'll want to click on that Nearpod link. We are going to be bouncing between the Nearpod and the notes here on OneNote a bit. I will, of course, push these OneNote notes out to you at the end so you have them. But please write a few things down as we go along, because you will want to have something in your notebook, I think, that is quite beneficial for you. So, probability. Common misconception about probability, all right? We humans think of probability on the short term. So it just seems so random, all right? What looks random in the short term, however, becomes very probable in the long term. All right. This is how actually casinos make money. All right. Casinos are all about the long game, not the short game. But their customers are all about the short game. So yes, a slot machine might give out $10,000 once. Okay. The company does not think, all right, well, we got to replace this slot machine. It gave out $10,000. No, that's short term. Okay, yes, people win in the short term, but they do not win in the long term, because that slot machine over a long period of time will definitely have more losers and make more money than it gives away money for winners. That's how casinos make all their money, is by people thinking they're winning in the short term, when in actuality they are losing in the long term. Because we all remember that one time we won $50 at blackjack or whatever it is. But we don't remember the 10 times we lost $10 at blackjack. All right? We just remember the one time where we won. That's how casinos make money, and probability is not random oftentimes in the long term. The short term, however, it does look extremely random and variable and unpredictable. So probability. A number between 0 and 1 that describes the proportion of times an outcome will occur in a very long series of trials. That's kind of a specific definition, technical even, but probability is a number between 0 and 1. It's basically a percent, right? What percent chance do you have? But we oftentimes report it as simply a decimal. So our first example is the most basic, flipping a coin. So of course, flipping a coin, we all know that probability is equal to 0.5, right? Right? It's 0.5. 50-50 chance of getting heads or getting tails. But if you flip a coin 10 times, do you think you're actually going to get exactly 5 heads and 5 tails every time? No, definitely not. With only 10 tries, you're going to have a lot of variability. And so I want you to try this. You're going to flip a digital coin 10 times. All right? And then you are going to report to me in the Nearpod how many of one side. It's a very apt coin for today. One side says, the hell with it, and the other side says, let's do this. I thought it was humorous, especially for today, being it election day. So you are going to flip that digital coin 10 times. It does 10 rolls for you all at once. And then you're going to report to me on the Nearpod. But the key here is, all right, for true random, you don't get to just keep clicking it until you see a good one and report back to me the good one. All right, that's not random. That's just choosing one you like. So we all got to just hit it once and then report the next one no matter what. Okay? So I'm going to count to 5. Then you all get to click roll again one more time. And then you have to report that one no matter what. Okay? So 1, 2, 3, 4, 5. Click it one more time. And then no matter what, you've got to report that one to me. In the Nearpod, the first slide should be, first slide should be how many the hell with it. It's called the decision-making coin. I hope your answer choices are in order. When I look at the results, my answer choices are definitely not in order. It goes 8, 9, 10, 2, 7, 3, 5, 4, 6. Oh, they are? Okay, good. I was afraid when I first pulled up mine, when I made it, I put them in order, certainly. But when I saw the live participation, they were not in order. I was like, really? You're killing me. All right, another second or two, let me share the results to you. Hopefully it's showing up on you, the little pie chart there. And so you can see we didn't all get 5, all right? There's a lot of variability here. Some people got only 4 5s. What's the biggest one we had? Nobody got 9, nobody got 8. So the most we got were some people got 7. Some people got 7, the hell with it, in one set of 10 rolls when we only expect to get 5. What was the smallest? Some people only got 2. So there's a wide range here of what you might get if you only flip the coin 10 times. Okay? It's random in the short term, but it becomes very predictable in the long term. This was a short term. So if I want to do this long term, I have to do a whole lot more than 10 flips of the coin. Then we will get to what we know the proportion is, 0.5, a 50-50 chance. All right, so that is what we're going to do next. All right, so I'm going to go to a website here. Come on back to my screen. We'll be flipping back between this and the Nearpod quite a bit. All right, so I'm going to do a simulation here of what you just did, the 10 coin flops. All right, so if I do 10... There we go. That is 10 coin flips. And as you can see, it jumps around away from the 0.5 proportion that we know. Now, in this case, we got 4 heads out of 10, which is pretty close to the 0.5. This is true. But sometimes we go all the way up to 0.8, all the way down to 0.4 for the proportion. It's definitely quite variable because that's the short term. It's too short term. We got to go long term. So I'm not going to go past 25, 50. I'm going to do 100 tosses. Now let's go 200. 200 tosses. And you're going to see that this line, while it does vary away from the 0.5 sometimes by quite a bit, in the long term, boom, we hit almost exactly a perfect proportion of 0.5. 105, oh, it's exactly at the very end. 105 out of 210 are heads, and 105 out of 210 are tails. Let me take a picture of that for us here. We'll put that in our OneNote, all right? No, where's OneNote? Here we are. So what does this picture show us right here? This shows us that in the short term, our proportion of heads or tails could be very far away from the true proportion, 0.5. But eventually, we will definitely get closer and closer to that true proportion of 0.5 that we know is what a heads or tails 50-50 guess is. All right, so this graph shows us that in the short term, the proportion of heads can be quite variable and far away from p equals 0.5. But in the long term, this proportion gets closer and closer to what we know it should be, which is p equals 0.5. And that phenomenon is what we call the law of large numbers, okay? The law of large numbers says after many trials, the proportion of an outcome will approach its true proportional value. It may take a lot of trials because at the beginning, the short term, there's lots of variation. Okay? But in the long run, it will eventually get to its true proportional value. Coins or anything else, that will happen. Okay? The law of large numbers. Yeah, this trial we did especially, man, that got down to 0.3 for the proportion of heads versus tails. That was actually quite a few trials in, too. That wasn't just like 10 flips of the dice. That was like 20 or 30 flips of the dice. Or flips of the coin, my bad. We'll do dice in a bit. This is getting dicey. All right, so just a few reminders about the numbers here. If you have a probability of 0, all right, that means this will never happen. All right, if your probability is 0, hopefully that makes sense. It can't and won't ever happen. A probability of 0.5, again, think of a probability like a percent. This has a 50% chance of happening. All right, like a coin flip, 50-50. And a 1, again, it's like a percent, so that would be 100%. All right, which means it will always happen. If you have a perfect 1 for your probability, it will always happen. And of course, in between, you have different percents, of course, but there's 3 references for you there, okay? All right. A few more Nearpod slides I'd like you to try out. I think there's a matching and a little quiz or something, a one question for you to think about. So head on over to the Nearpod. Again, let me give you 4 or 5 minutes. That's probably plenty of time. Take a look at those 2 slides. Slides 2 and 3. Make sure you are with me still. Oh, my bad. I gotta switch it, don't I? Sorry about that. It still trips me out. It took you 6 tries to get that? No. I feel like I should write them a memo. I can't show you the answers, can I? So again, short story here. If you're closer to 0, much less likely to happen. Closer to 1, much more likely to happen there. All right, looks like most of us got those there. Sweet deal. All right, next slide here. This is a great old-timey myth here. 7 kids in general terrifies me. Man, I would never want to be outnumbered. That's why I always tell people, I don't want to be outnumbered. 2, I'm partial, I know, but 2 was enough. Man, I do not want to be outnumbered. 2 is more than twice as hard as 1. And I hear that 3 is a lot harder than 2. Well, yeah, but you're all grown up and you listen. It's a funny thing as a parent and a teacher right now, I have a lot less patience with my own children because, like, when I'm in a classroom, I'm like, all right, everybody, flip to page 28. Let's take a look at problem number 2. And you know what happens in the classroom? Everybody does it. Like, within, 10 seconds, probably? But when I talk to my kids, I'm like, all right, go brush your teeth. And then 10 seconds later, they still haven't done it. Like the teacher mode going, I'm like, what the heck? I told you 10 seconds ago to go brush your teeth. They're like, Dad, it's been 10 seconds, man. Come on. I was like, I'm in teacher mode. All right? We got things to do. What do I care if it takes you 15 minutes to brush your teeth? Where else I got to be? But yeah, it's an interesting dynamic. But back to our male-female thing here. Studies have shown that your previous gender babies have nothing to do with your subsequent ones. They are independent events is what they're called in probability. We'll get to that a little bit later. But they are independent. One has no bearing on the other. In coin flipping, you'll sometimes hear that coins have no memory. Okay? If you flip a coin over and over again, and let's say you get 5 tails in a row, 5 tails, tails, the next throw is still a 50-50 chance. And so you could very easily get 5 tails in a row or 7 tails in a row sometimes if you do it enough. And so it's not that unlikely that some people might have 7 girls with a perfect 50-50 chance of boy-girl possibilities. It definitely will sometimes happen. All right. What can we do with this? All right. What can we do with all this probability mumbo jumbo? Well, in stats, we use it to run simulations. Okay. So head on back to the OneNote here with me. Our next example is about simulations. You need to be able to design and run what we call a simulation. We've done this a little bit. We just touched on it very briefly in the last unit. There was like 1 or 2 examples, but here we really start doing it in earnest. So a simulation simply imitates a random process. So here we go. 1 in 6 wins. Coca-Cola is running a special promotion. Boy, you really like Coca-Cola, don't you? Yes, it's pretty good. Much better than Pepsi, don't you think? You have a chance at winning a prize with each bottle you buy. Under the cap, it will either say, you're a winner, or please try again. You can't tell the difference between the two. You know it. All right? That'd be a fun experiment to do. Can people actually tell the difference in a blind test which one is Pepsi and which one is Coke? It'd be interesting. So, we would actually, our control there would be a simulation. So a statistics class decides to test this. All 30 students in the class go out and buy 1 bottle of Coke. And only 2 of them get caps that say you're a winner. Is the company lying to us? I mean, we would expect, if it's truly a 1 in 6 chance, and we had 30 students go and buy them, we would expect 5. Right, 5 times 6 is 30. We would expect 5, but we only got 2. So are they cheating us? Well, we could go do the experiment again and go buy another 30 Cokes. Try again, and then again and again, and keep feeding our money to Coca-Cola Corporation so they can rule our lives like Google and Amazon do. That's too expensive. All right, so what we do is we make a simulation and we let random numbers generate this over and over again using a 1 in 6 chance. All right, so Here's one of the things you have to be able to do to describe a simulation. We will model this scenario using a simulation of a 1 in 6 chance using a 6-sided dice. Simulation. All right, so we're going to use a 6-sided dice. That gives us a random chance to do this. Now we have to label this dice. All right, so we will label 1 through 5 as please try again, and a 6 as you're a winner. Yay. All right. So that way, as we roll the dice, a 1 through 5 represent losing, and a 6 represents winning. Now, the other thing you have to do in describing a simulation is describe what you are going to record. All right, so we will roll the dice 30 times and record how many 6s there are. All right, because every time we roll a 6, that's a win. And we're going to do it 30 times because we had 30 students. And see, is it crazy rare to only get 2 wins out of 30 trials? All right, out of 30 rolls of the dice, is it super rare to only get 2 6s? So again, you do need to, in your scenario, in your simulation, you have to label what is what. Okay, so I labeled 1 through 5 as please try again, and 6 as your winner. Then you also have to communicate what you are going to record. We are going to record how many 6s there are. All right, let's do this. All right, thankfully the internet can do this for us, so you don't actually have to roll a dice 30 times. Okay, so into the chat, here goes your link to roll a dice 30 times. Now again, you can't just click roll again until you see a good one. All right, you don't get to pick which one you do. All right, so you have to think, all right, the next one I'm going to record, hit roll, and then you're going to record that one. Now, how are you going to give me these results so we can put them all together? This link right here will take you to a Microsoft Forms where you can report to me the number you got. Okay, so I'm going to do one quick example on my screen, and then you're going to do, I want you to do at least 2 or 3 or 4 times so we get lots of good data. So first, here is what the dice looks like. I'm going to hit roll again to give myself a roll. And now I got to count the 6s. 1, 2, 3, 4, 5, 6. So I got 6 6s. So now I'm going to come to the Microsoft Forms. I clicked on the link for Microsoft Forms. I got 6, and I'm going to submit it. And then do it 2 or 3 times for me. So you can click submit another response once you do it again. So hit roll again, and then count up the 6s. 1, 2, 3. All right. I only got 3 that time. Yeah. All right. So now I'm going to go back here, submit another response. I only got 3 that time. Do that 2 or 3 more times for me. Get me some good data, and we will see with all of these trials in our simulation, how likely is it that you'll only get 2 wins? Ooh, I got lots of responses now. I'm not deleting the data, so you also have third period's data here. So we're going to have a nice big data set here. You got 0? Oh, I didn't put a 0 on there. I think I can fix that. Joel, give me 1 second here. I think I can update. Add option 0. Can I move it to the top? I can move it to the top. All right, saving, saved. All right, you might need to refresh, Joel, but you should be able to put in the 0 now. I didn't think about not getting any. Pretty rare, but it could happen. Yeah, there it goes. Sweet. All right, 3, 2, 1. If you haven't taken a look at the data set on my screen, come take a look at our results here. Oh, what in the world? Did I really? Oh, it took it right when somebody responded. There it goes. There we are. As you can see, there's definitely a peak around 5. All right, there's definitely a peak around 5 here. 4 and 5 and 6 actually are all fairly likely. And then it tapers off pretty quickly above and below that. But we're just interested in how likely is it that you would only get 2, or actually 2 or fewer, because those are also just less likely as well. That would also seem like the company is cheating us. And as we can see, 2 or fewer, 16, 21, 22, 22 times we had 2 or fewer winners. 22 out of 164. What is 22 out of 164? 22 out of 164 is about 13%. 13% of the time you'll have 2 or fewer winners in a group of 30. Well, that seems perfectly plausible. I mean, is it kind of rare-ish, I guess? It's not going to happen all the time, but it's not just so far out that we think Coca-Cola is cheating us. I mean, they're cheating us in many other ways. Don't worry about it. They're rotting our teeth, making us gain weight, all that horrible stuff. But in this case, they're not cheating us here. All right, so let me put that in right here. There are the results of our simulation. Let's write what those mean. So in our simulation, there were 22 out of 164 times that a group of 30 had 2 or fewer winners. So, I mean, this is about 13% of the time. So it is very plausible that it could happen when the chances are 1 in 6 are winners. So Coca-Cola is probably not cheating us. All right. Our observed 2 out of 30 could definitely happen. 13% of the time it will happen. So we don't really believe they are cheating us here. So instead of buying Coke over and over and over again, that is our simulation that can do it for us. All right, let's take a look at another example. Writing a simulation is kind of hard to do. It's going to take some practice, and so that's, kind of what we're going to do right now is practice writing a simulation. So, here's the next one. In an attempt to increase sales, a breakfast cereal company decided to offer a NASCAR promotion. Each box of cereal will contain a collectible card featuring one of the following NASCAR drivers. That person, that person, that person, that person, and that person. Any NASCAR fans out there? I don't follow. I recognize Danica Patrick. I mean, she's definitely more famous than most, I'm guessing. But I don't recognize the other. I don't follow NASCAR. It's a big sport, apparently, though. The company claims that each of the 5 cards is equally likely to appear in any box. All right, so wait, hold on. We got 5 cards. They're saying each one is equally likely. That's a 1/5 chance to get each one of them. So a fan decides to keep buying the boxes of cereal until she has all 5 drivers' cards. She is surprised when it takes her 23 boxes to get the full set of cards. Does this outcome provide convincing evidence that the 5 cards are not equally likely? All right, is it not actually a 1 in 5 chance to get each one of them? To help answer this question, we want to perform a simulation to estimate the probability that it will take 23 or more boxes to get a full set of 5 NASCAR collectible cards. All right, so yeah, how likely is it that it would have taken 23 or more times? Because that does seem excessive, doesn't it? So the first thing we're going to do is describe how to use a random number generator to perform one trial of the simulation. Then we'll do this. Oh, and then we'll use their dot plot because they did the simulation for us. So first, A. Describe a simulation here. So what we're going to do, we're going to use a random number generator to generate random numbers from 1 to 5. We got 5 people. So give each driver a number from 1 to 5. Then generate random numbers from 1 to 5 until each number appears. All right, because we want to keep buying cereal until we get all 5 drivers. So we have to generate random numbers from 1 to 5 until we get a 1, a 2, a 3, a 4, and a 5. Now, what are we going to record? Remember, we can't just describe what we're going to do. We have to describe what we're going to record. We will record the number of times it takes to get all 5 numbers. All right, how many times does it take to get all 5 numbers? Let me show you one of those, what that might look like here. Where's clear? There it is. So I'm going to go settings, or there, probability, random integer from 1 to 5. All right, so I got the 2. Oh, shoot. No, that doesn't know. Oh, now I got the 4. Now I got the 1. I need the 3 and the 5 still. I got the 5. Now I need the 3 still. Yeah, I finally got the 3. All right, so I did my random number generating. I now would have to record the number of times I had to do that to get all 5. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. It took me 12 times to get all 5 numbers. And I know that that was a perfect chance. A 20% chance? A 20% chance to get all of those, to get each number individually. But it still took me 12 times. And so as you can see, I could have then added a dot, 10, 11, 12. I could have added a dot, or I might as well do that, eh? Why not? Add a dot right here at 12, because that was the one I did in the simulation. But they thankfully did this 50 times for us already. I appreciate that. Starnes, and Starnes. I think that's who wrote the book. All right, so letter B. Explain what the dot at 20 represents. So there's one dot over here at 20. What does that represent? So that means that in one trial, it took 20 times to get all 5 numbers, aka drivers. They had to randomly generate a number 20 times before they got all 5. So each dot does not represent 1. It represents getting all 5 numbers, a whole sample or a whole trial of your simulation. All right, and C then. Use the results of the simulation to estimate the probability that it will take 23 or more boxes to get a full set of cards. All right, so where is 23 here? And I think we got an issue there, don't we? I don't think there is a 23 on that graph. Let me draw on there. So this would be 21, 22. Yeah, it never happened. There is nothing up there. This never happened. If there was actually a fair 1 in 5 chance, our simulation says that it should never take 23 or more times. So in our simulation, it never took 23 or more trials to get all 5 drivers. So what does that tell us? This means there is probably not an equal chance at getting of getting each driver. And we should all kind of intuitively know that. Cereal companies always make one of the prizes super rare. We've all played, have you played the McDonald's Monopoly? Is that still a thing? Man, I remember that was first a thing. McDonald's Monopoly. It's like, man, I just need Park Place and I win $1 million. There's only 2 of them. It's a 50-50 chance then, right? If there's only 2? No. One of those is very unlikely to happen compared to the other. Okay? And so that's kind of what we proved here. They are not all equally likely to happen. One of them is probably, one or more is more rare, which is why it took 23. Great story, actually. If you want to go on a Wikipedia rabbit hole or something on the internet, look up the $1 million winners for the McDonald's Monopoly. Huge scandal, by the way. Huge scandal. It's a good read sometime. Go look it up. All right, another one. Let's do this. This one you're going to kind of do on your own with Nearpod, all right? So I'll read the example, then we're going to head over to Nearpod, and you're going to do it. A local high school. Yeah, we got 10 minutes. We got enough time to do one more. 95 students have permission to park on campus. Each month, the student council holds a golden ticket lottery at a school assembly. The 2 lucky winners are given reserved parking spots next to the school's main entrance. Just like Charlie and the Chocolate Factory, man. Last month, the winning tickets were drawn by a student council member from the AP Stats class. When both golden tickets went to members of that same class, some people thought the lottery had been rigged. Sounds like something the AP Stats class would do, too. There are 28 students in the AP Stats class, all of whom are eligible to park on campus. We want to perform a simulation to estimate the probability that a fair lottery would result in 2 winners from the same AP Stats class. Okay, how likely would it have been that out of 95 people, that 2 of the same kids from the same 28 student AP Stats class would get the golden ticket? So it is kind of hard to write these simulations. So your first one here, I help you out a bit. So head on to the Nearpod, and I will advance you forward. Where's Nearpod? There we are. Fill in the blanks to write that simulation. So I'm going to do a few of these trials here, 10 at a time. And so you would take a number between 1 and 95, right? Because we got 95 people that are possibly going to be selected. But we need some way to distinguish the 28 stat students. So we'll just say from 1 to 28, those are the stats kids, and then everything after that are the other students. So when I generate a bunch of random numbers, I got pairs here because I have 2 students, right? Nope, not AP stats. No. Oh, one of them was only one. I'm looking for a pair where both of them are 28 or under. So in those 10, I didn't get any. All right, so I try again. No. Wait, there's one. 18 and 27, those are both less than 28. So I'm recording whenever I get 2 AP stat students. So that'd be 1 right there. I got 1 success, essentially, that I can record. No. So right now I'm at 1 out of 20. I've done it 20 times, and I've gotten 1 success. Oh, there's one. No. All right, so now I'm at 2 out of 30. I've generated 30 pairs, but I've gotten 2 successes. Let's do this one more time. No. What? Yep. That one's good, right? Yeah. I got 1 success there. All right, so now I'm at what? 3 out of 30 or 3 out of 40? I was 2 out of 30 before. Now I'm 3 out of 40. All right, 3 out of 40. 3 divided by 40. About 7%, 7.5%. So is it 7.5%? Is it completely unbelievable that the 2 students picked might be from the same AP Stats class? Not really. For the ones I just did, it happens about 7.5% of the time. Not crazy, unbelievable. Okay, it can happen. It will happen 7.5% of the time if you did many trials. Okay. Now, I only did it a couple of times there. 40 trials is not getting towards the law of large numbers yet. So who knows? Maybe my fluctuation was still misleading me a little bit. But I don't think the AP Stats class was cheating us. All right. So what do we got to be able to do now, ladies and gentlemen? You got to be able to write a simulation. So when I pass this OneNote out to you, you'll have those examples. You wrote one on the Nearpod. Hopefully you are kind of seeing how that goes. I also want you to have a good understanding about the law of large numbers. Okay? That a true proportion in probability only really happens after many trials. That's why we do the simulation with many trials, to see what the true proportions will be. In the short term, things are very variable. So when you see one trial, like we got 2 wins out of 30 people that did their Coca-Cola thing, that could be extremely variable. I don't know if that's evidence to say that they're cheating us, because it could be very off from the true proportion right now, because it was a short-term idea. We have to do many trials to see if that is, in fact, just variability or if the actual proportion is different. All right, there will be a lesson coming up this afternoon. I've got it written. I just have to record it, and hopefully that won't take too long this afternoon, so you'll still have tonight to work on that if you like. But also some book problems. Again, ladies and gentlemen, they're all odd numbers. This is not a test. You need to try those out, look at the answers, and understand those problems. Okay? You need to be able to understand what each of those are talking about. That's the whole goal of homework. All right, ladies and gentlemen, that is it for me. Have a great, great day. I will see you on Friday. Woo! Hopefully the world is not burning by then.
Thanks, Mr. Bolt. Have a nice day.
You too, you too.
Hi, Mr. Bull. Have a good day.
I will if you will. Oops, stop recording.